Hi, I'm Peter Oram, and I'm here to introduce you to something impossible. This is all about energy and how to shape, store, and release it. I'm going to touch on these topics. We heated an LED to 202 degrees C and observed the light it gave off. We measured the temperature of the light as shown above. The light temperature was much hotter than 200 degrees C, even with zero bias. The temperature difference had to be self-establishing. If there's a temperature difference, we can run a heat engine. This is the basis of our device. So, semiconductor heat engines. On the left is a typical thermoelectric device. On the right is an ATEC device, which looks very much like an unwound thermoelectric device. Here are my prototypes. There are 3 of them visible, one of which is measured. They're actually about 4 microns thick. And here is my voltmeter. Now I'm going to switch the leads, and the polarity is going to reverse. It was 11 microvolts before, now it's minus 12 after switching the leads. This touches nearly everything. For various energy sectors, we think we can touch 70 to 99% of the use cases. For an electrically driven process, we can often take recovered heat and feed it back into the process. Here's our roadmap to a marketable device. The next 3 rounds of prototyping should bring it to where an increased layer count will give 1.5 volt output and at least 100 milliwatts of power. After that, we know how to contract for production. Let's talk about the range of usefulness. It runs from frozen to inferno, with almost everything in between. If your mission calls for deployment to hell, we have you covered. There are many different things we can do with this. In many cases, the biggest limit is ice formation. As long as we can manage that, we can supply power. If you don't see your use case, we can probably sketch it out for you. Here are some use case sketches. Using heat sinks and airflow to cool electronic devices is bulky and wastes energy. The first stage of improvement is to mount and wire ATEC devices to the back of PC boards to convert heat into electricity, then feed the electricity back into the power supply. The second stage is to build ATECs into hot chips, such as processors. On a larger scale, ATEC-based cooling for air conditioners and server farms will move these facilities to net zero energy operation. Pumped water storage is used to capture peak solar and wind generation and tap it to serve peak load. Efficiency of the cycle is around 70%. ATECs can be used to extract thermal energy from water to do the lifting. Recall that a BTU heats 1 pound of water by 1 degree Fahrenheit and is 778 foot-pounds. So each unit of water has enough energy to lift it 778 feet per degree Fahrenheit. If you consider that the reservoirs act as reheating ponds, efficiency could climb to well over 100%. Let's follow that thinking along and eliminate the vertical pumping. We need to move water across ATEC-clad surfaces. Let's just make electrically driven ATEC-clad propellers in lakes or other bodies of water, draw off electricity, and let the sun rewarm the water. Let's apply that same principle to raising groundwater, filling irrigation canals, and water distribution pipes. Let's use water's own thermal energy to move it around, rewarming as needed from the environment. As great as they are for efficiencies, LEDs still lose over 2/3 of the energy into them as heat. ATECs can capture that heat and recycle it back into electricity, even within the immediate LED. Water can provide the energy needed for most ship propulsion, even in water as cold as 1 degree C. In this use case, our Navy would like to manage air temperature and humidity in its ships. The ATEC-based unit in the upper left chills input air to remove excess water and then reheats the drier air from ATEC-supplied electricity. Excess heat could be dumped outside with resistance heaters. A shortfall of energy can be restored through the ship's hull. Industrial processes use and lose about a third of the total energy in the United States. Most of it could be recovered by ATECs and recycled back into the processes. This assembly would look familiar if we had drawn it as a AA battery. There's a positive and negative terminal. Inside is an ATEC that can produce 100 milliwatts at 1.5 volts. Put an electrical load on it and it will run forever. Of course it will get cool, so you need to give it access to its thermal environment. This assembly of ATEC devices embedded in a rollable package could supply a kilowatt of electricity to streamside campers. With its high specific heat, availability, and cost, water is a great storage medium for energy. Peak solar or wind energy could be captured with resistance heating and converted back to electricity with ATECs. Air-sourced ATECs may be cheaper than solar or wind collectors. There are literally billions of users of portable and fixed electronics and Internet of Things and agricultural installations who need just a few watts or less to run their devices for long times without worrying about power. ATEC power will work for them. Ride a motorcycle? You'll want this to keep cool in summer heat. On a battlefield in full kit? There too. We at ThermoWatts thank you for watching this presentation. Do you have any questions about our technology? Do you have a challenging use case you would like to discuss, especially if you need cheap, portable, clean, safe power?